Hey guys, I'm Josh Myers and I'm bringing you another chemistry video on behalf of Academia on Demand. So today we are going to be talking about the trends and of how the elemental properties apply to the periodic table, most specifically down a group and across a period. So before we go into the properties that we talked about in the last video, we are going to review what makes the elements within a group and within a period special. And this is where we talk about electrons. So across a period, period 2, all of these elements have their outermost energy level being 2, meaning that the most outward energy level from the nucleus, the second energy level, that is the most outwards energy level that contains electrons. Now, down a group. A group represents all of the elements within a group possess the same number of valence electrons, but in a different energy level. So in the first period of the first group, that is hydrogen. 1, as we see, that is hydrogen, and it contains 1 valence electron in the first energy level. Lithium, 1 valence electron in the second energy level. And this is how we see that the group corresponds to the valence electrons while the period corresponds to the energy level. Okay, so now let's talk about the properties that we brought up in the last video. So the properties, the elemental properties, characteristic to every element. Okay, so now the first one is ionization energy. Ionization energy, and that, as we talked about, is the energy required to remove an electron from the valence energy level. Now we also talked about the atomic radius, AR, and that is the distance between the center of the nucleus and approximately the outermost energy level. However, as we discussed before, it can only be measured when an element is bonded to itself, which means that they measure the halfway distance in this bond, and that is how scientists are able to discover the atomic radius. Now finally, we are also talking about the electron affinity, which is the energy released. The energy released when an electron is accepted by an atom. So when an electron enters and stays in the valence energy level. And I emphasize the word released because energy is actually stored between this electron, the attraction between this electron and the positively charged nucleus. And so this stabilizes the atom, electron affinity. And so now the last one, the holy grail of all of these properties, the one we'll talk about the most, is electronegativity. Okay, so now the first thing we need to do is to really break down exactly why this group and why this period thing, why it applies to these ideas. And so the easiest way to do this is to talk about atomic radius first, because then we can draw a nice picture, and pictures always help us understand. And then these ideas, that once we establish the idea behind atomic radius, a lot of the other ideas with the other elements will make a lot more sense. So the atomic radius, and now we are going to I'm going to give you the trend right away. I'm going to say whether it increases or decreases down the group and across the period, and then we're going to talk rationale, because rationale is always the most important thing behind science. It is why we take experimental evidence and then we create theory from it. It is the theory that is the why. Okay, so down a group, and we are going to box this up so it's not confused with that arrow. Down group equals an increase in atomic radius. And now across a period, box that up again, period, across a period, equals a decrease in atomic radius. So the first portion that we're going to talk about, and the why, again, so important, the why, is the down a group option. And it's actually interesting because talking about why the elements, as you go down group 1, the atomic radius increases, is due to the period number. So as you go down the group 1, the period number of each element increases by 1. And as we talked about, the period is representative of the outermost energy level that contains an electron for that element. So if we draw our picture of a hydrogen, and we are actually just going to assume that this is a hydrogen nucleus. We're going to write H. We are going to write H instead of proton, and we will see exactly why this makes sense from an organizational standpoint later. Okay, so energy level. And we know that it contains 1 electron. We will really be talking a lot about the electrons in this video. So it contains 1 electron, and so as we know, roughly the atomic radius is the distance from this 1 proton to this 1 electron. And so that is this, that is this. But now let's go down one. Let's draw the structure of lithium. And this will almost intuitively make sense when we draw this picture. When we use this model of circular energy levels that I have been accepting throughout this channel so far. What I have said is the right way to do it throughout this channel. You guys know no different, I know it. Okay. Alright, so the second energy level, and we know, as we know, lithium has 3 electrons, so it completes the first energy level, and then it adds an electron right over here. And so as we can see visually, this model that we've been using visually displays this idea very easily. The atomic radius has increased. It has expanded outwards. It has expanded outwards, and if we were to do sodium, we would find the same thing. It would have this energy level, and it would do this, and it would keep going outwards. And so visually, this is a very, very simple idea to understand. Very, very simple idea to understand. And so now why does the atomic radius decrease across the period? Let's actually leave this picture because it will be very valuable later. Very valuable later, and that's not a hydrogen anymore, but you know what I'm doing. Okay, so across the period. Well, as we know, across the period, number of electrons, and the number of protons, so plus the number of protons increases. Let's do this little interesting swirl thing. Increases by 1 each time. ET, phone, home, ET, each time. Okay, and so this is actually pretty interesting because it would seem as though the trend is counterintuitive. It would seem as though as you add more electrons, as you add more valence electrons, the atomic radius would increase. This is actually not the case as we're seeing here. And the reason for this is that all of the electrons are added to the same energy level. So if we were to go back to this picture, there's no expansion outwards. You're simply adding more. You're simply adding more. And so all that this does is that it just, as we will learn in the orbital video, it stabilizes this energy level. It makes the energy level more stable. So it does not actually affect the atomic radius at all. But what changes, what makes across the period from lithium to neon, what makes the neon atomic radius less than the lithium atomic radius is that the number of protons increases. And why this is important is because when we look at the pull of the nucleus on the electrons, we look at ratios. And so given that from lithium to neon, all the electrons, all the valence electrons are in the same energy level, we look at the ratio between the number of electrons and the number of protons, and specifically how many protons there are to pull these electrons in. So as we know, This neon atom has 10 protons. It is atomic number 10. Atomic number 10. And whereas lithium is atomic number 3, which means that it has 3 protons. And so lithium has 3 electrons to 3 protons. Whereas neon has 10 electrons to 10 protons. And now this also may seem a bit confusing. The idea that they're both a 1-to-1 ratio when simplified. And that just because you add protons, you're also adding electrons. So it would seem as though perhaps they would counterbalance each other. But it's actually contrary. The idea that the electrons and protons attract each other, the addition of more of them in the same energy level, so it's not getting bigger, it's staying the same size. The addition of more electrons and more protons means more attraction, which means that this energy level is, if you wanted to base it off of this picture, you would think of it as pulled inward slightly. Pulled inward slightly, and thus the atomic radius decreases. It decreases. So taking this idea of what we call this idea of the number of protons, then the number of protons, the idea of where shall I write it? It is a massively important word. Let's erase y. You guys know we have to ask why. Okay. The reason for the decrease in atomic radius across a period most simply can be summed up in 3 words, and it is an increase in nuclear core charge. And so in this, again, just represents the increase in that nuclear pull on the electrons, that positive charge in the nucleus as the number of protons increases. Okay, so now let's talk about ionization energy. We will actually find that many of the same ideas that we talked about in the atomic radius section are actually very applicable to this ionization energy section, because I've already been talking for a very long time, so we need to really get down to work here. Okay, so ionization energy. And now I'm going to erase this. Did I move you? No, you can see everything. Okay. All right, let's get rid of all this because we need to make sure. We need to keep this picture. This picture is actually totally perfect. But we need to get rid of this. We need to erase. As we would say in Canada, erase. Okay. Almost done. This board really does get stained after a while. A lot of work, sweat and tears poured out onto this thing. You guys on your papers, I'm sure it's the exact same thing. Okay. Alright, so down a group would state the rule that the ionization energy down a group decreases. The amount of energy required to pull an electron off of the valence energy level of lithium is more. It is more than the ionization energy, the amount of energy required to pull this same electron, this valence electron, off of sodium. And we can talk about this a lot in terms of physics, and we will do this. And now across the period from lithium to neon, the ionization energy increases. And we can actually relate this completely to physics. We don't even really need to draw out another picture. But all we have to really understand is that if we talk about the formula for electrical energy, and this is where we cross sciences a little bit. If we say electrical energy is equal to Coulomb's constant multiplied by Q1 times Q2 divided by r. This is the big one, divided by r. And so this formula represents the electrical energy between two charges, so between an electron and a proton in the nucleus, as dependent, actually inversely proportional to the radius. And this is why when we had the radius, this was up, that was down, whereas when we have ionization, that is down and this is up, because they are inversely proportional. Inversely proportional. And if we think about this, as we move down a group, the number of energy levels increases. So the atomic radius increases, which makes the ionization energy, because as we know, ionization energy go down, because as we know, we talked about in the last video, the amount of energy required to pull this electron, to give it enough kinetic energy to break its attraction with the nucleus, is equal to the amount of energy, the electrical energy in the attraction between the nucleus and the electron. And so therefore, if the radius increases, this electrical energy attraction between the nucleus and the electron decreases. So if you increase the energy levels, this increases the radius, therefore decreases the ionization energy. Conversely, if you move across the period, these electrons are pulled in by the nuclear core charge, and thus the ionization energy increases because the radius decreases. So let's actually just leave that formula there, because it will work. It will tell us a lot about almost all of the other properties. So electron affinity. Let's talk about electron affinity. It turns out that electron affinity actually has the exact same trends as ionization energy. It turns out that electronegativity also has these exact same trends. So atomic radius turns out to be a little bit on its own. That's okay, because it tells us the most in the form of a picture. Okay, so let's talk about electron affinity. So electron affinity, as we said in the previous video and now in this video, is the idea that it is the energy release, is the energy that is created between when an electron is accepting the valence energy level, the energy between this electron and the nucleus. So when you move down the group, as we know, the energy level increases. And so therefore, if it were to accept another electron right now, if lithium were to accept another electron, it would take on a certain amount of energy. And because we know this electron is in the second energy level, it has a specific radius. Whereas if sodium were to accept this electron, this radius that this electron would be from the nucleus would be bigger. It would be a larger radius, which means that the amount of energy between this electron and the nucleus would decrease, which is exactly what we're talking about when we talk about electron affinity. And so down the group, because of this increase in the radius, the increase in the energy level, the electron affinity will go down as well. The period, and I just realized I actually spelled period wrong. That is pretty funny, actually. Period, okay. Period, because I'm a hockey player and there are 3 periods in a game. And so across the period, same thing, exactly same thing, where the radius across a period decreases, and so the electrical energy between an electron that is accepted in this energy level will actually increase. It will increase relative to the third period, where this electron would be in the third energy level, so it would be further away from the nucleus. Oh no, sorry, no. It's in the second energy level, because as we know, as you move from boron to carbon, and then from carbon to nitrogen, and from oxygen to, and then from nitrogen to oxygen, we know that the atomic radius goes down. It decreases a little bit each time because the nuclear core charge pulls it in. It makes it more compact. And so now if electron were to be accepted in this more compact state, let's say oxygen accepts an electron in its compact state, the electron would be accepted in a certain radius. But say nitrogen accepted this electron. The radius in this nitrogen atom is already slightly larger than the one in the oxygen atom, which means that the energy between this newly accepted electron in the nucleus will be greater for the nitrogen than the oxygen. And now finally, this video is getting very long, so I gotta wrap it up. Okay, so now the electronegativity. Electronegativity is the tendency of an atom to attract bonding pairs of electrons, and that's why it's so important, because we talk about electronegativity and bonding. But really it is simply the ability of the nucleus to attract electrons into the valence energy level, because as we know, anytime an electron is accepted by an atom, it enters the outermost energy level, the valence energy level. Okay, and so we know that the attraction of the nucleus, for the lithium atom, will be greater for electrons that are entering its possibility, the possibility of bonding with them, because the radius is smaller. So we know that it will attract electrons easier than sodium, easier than potassium, because as the radius gets bigger, the ability to attract gets smaller. And so as you move across a group, we know that the atomic radius decreases, the nuclear core charge increases, and this is the same idea that oxygen relative to fluorine is able to attract these electrons easier because its atomic radius is smaller. And as well, it has the ability that if it accepts an electron to gain a more energetically stable state, being the same electron configuration as neon, it is considered stabilized in this state. So now we will talk about orbitals in the next video, which will tell us a lot more about why this stabilization occurs, why this stabilization is very, very relevant to these properties, and then later to bonding. See you, everyone.